For the last 60 years, the entire global tech economy has operated under one unbreakable law of physics. You cannot build a transistor smaller than 1 nanometer. If you try, electricity loses its mind. It leaks, it overheats, and quantum tunneling tears the microchip apart. TSMC said it couldn't be done. Intel claimed it was a decades-long bottleneck. But just days ago, IBM did the unthinkable. They didn't just break the 1 nanometer barrier, they completely demolished it. By unveiling the world's first 0.7 nanometer processor architecture, the nanometer era is officially over. The era of the atom has begun, and the global semiconductor power balance will never be the same again. Before we dive into the exact engineering magic behind this atomic shift, I want to ask you a fast question. Let me know down in the comments right now. Do you think Intel and TSMC are officially in trouble, or can they pivot fast enough to survive this? Type it out right now. I want to see your predictions because the answer might shock you. Because while you type that, the reality is that the top executives at those trillion-dollar foundries are facing a sudden, secret emergency. To understand why the entire hardware industry is currently in a state of absolute panic, you have to look at the massive wall the world's biggest chip manufacturers have been crashing into. For decades, companies like TSMC, Intel, and Samsung have grown trillions of dollars larger by following a simple rule known as Moore's Law. Shrink the components, double the performance, and do it every 2 years. But we hit a physical limit. In modern advanced nodes like TSMC's 3 nanometer or Intel's upcoming 18A processes, the components are already so incredibly small that they are measured by the width of individual DNA strands. At this scale, silicon stops behaving like a predictable highway for electricity. Instead, a nightmare phenomenon called quantum tunneling takes over. When the gate, the physical switch that turns a transistor on and off, becomes less than 1 nanometer thick, the electrons don't wait for the switch to open. They literally teleport through the barrier. It is the physics equivalent of a car driving straight through a solid concrete wall. This causes massive current leakage, catastrophic heat generation, and unpredictable data errors. For the last 5 years, contract manufacturing giants have quietly admitted that traditional chip scaling was running out of runway. If we couldn't go smaller, artificial intelligence, supercomputing, and consumer hardware would stall out entirely. But the engineers at IBM quickly realized they had accidentally opened up a completely different path, one that would solve the crisis by throwing out 60 years of traditional silicon design. Enter IBM Research. Deep inside their elite cleanrooms in Albany, New York, a team of engineers realized that the only way to keep scaling was to stop thinking flat. For the past 60 years, transistors have been laid out side by side in a two-dimensional plane across the surface of a silicon wafer. Even the latest gate-all-around nanosheet technologies, which surround the electrical channel on all sides, are placed flat next to each other. When you run out of space in a crowded city, you don't keep spreading outward, you build skyscrapers. IBM's breakthrough is a radical new three-dimensional transistor architecture called the Nanostack. With the Nanostack, IBM has officially unlocked the Z-axis of computer engineering. Instead of placing the two core types of transistors, the N-type and the P-type, side by side on a flat surface, IBM figured out how to vertically stack and stagger them directly on top of one another like bricks. If you are the kind of tech enthusiast who wants to track these quiet hardware wars before the mainstream media even notices, hit the subscribe button right now. We track the raw laboratory breakthroughs every single week so you always know what's coming next before it hits store shelves. By stacking these nanosheets vertically, using advanced three-dimensional sequential integration, IBM has achieved an architectural miracle. They have packed nearly 100 billion transistors into an area roughly the size of a single human fingernail. That is nearly double the density of IBM's milestone 2 nanometer chip. To fully grasp the sheer scale of what IBM has achieved in Albany, we have to look closely at the atomic architecture of the Nanostack itself. In a standard advanced chip layout, the manufacturing process relies on something called complementary metal oxide semiconductor technology, or CMOS. A CMOS circuit requires both an N-channel transistor, which carries negative electron charges, and a P-channel transistor, which carries positive holes. Traditionally, these two types of switches sit side by side on a flat silicon plane. As you try to push the node down toward 2 nanometers and below, the physical isolation distance between the N-channel and the P-channel becomes dangerously narrow. If they get too close, they suffer from catastrophic electrical crosstalk, short circuits, and parasitic capacitance, which slows down the entire processor. The industry attempted to solve this by creating forksheet transistors, where a microscopic wall of dielectric material is shoved between the two channels to keep them separated. But even forksheets reached a dead end because you still had to waste massive amounts of horizontal space on the wafer just to build those isolation walls. IBM's Nanostack bypasses this entire limitation by taking the P-channel transistor and literally floating it directly on top of the N-channel transistor. By stacking them vertically, the horizontal footprint required for a single CMOS logic cell is cut exactly in half. This is the secret mechanism that allowed IBM to reach an unprecedented density of nearly 100 billion transistors on a fingernail-sized piece of material. But the engineers quickly realized that this vertical scaling had accidentally triggered a massive hidden benefit for the ongoing artificial intelligence gold rush, one that bypasses the single biggest blind spot in modern computer science. Most people think AI speed depends entirely on the raw performance of a GPU, like NVIDIA's Blackwell clusters. But they are completely wrong. Let me ask you another quick question. Did you know about the hidden SRAM memory wall before today? Because right now, the single biggest bottleneck holding back massive AI workloads isn't the processing core itself. It is memory bandwidth. Supercomputers waste immense amounts of time and energy waiting for data to travel from the storage memory to the logic processor. To fix this, chipmakers use a highly coveted ultra-fast type of memory called SRAM, or static random access memory, which sits directly alongside the main processing cores. The problem? While logic transistors have successfully shrunk over the years, SRAM has refused to scale. It is notoriously stubborn, taking up massive amounts of precious real estate on modern silicon. It has stagnated for over a decade. IBM's Nanostack architecture completely solved this crisis, achieving a massive 40% scaling reduction in SRAM circuits. By shrinking the memory footprint by nearly half, chip designers can now place massive amounts of high-speed memory cache directly on top of the logic gates. This means AI models can be trained and executed at speeds that were previously considered mathematically impossible, removing the data traffic jams that plague modern server racks. In fact, internal estimates indicate that AI accelerators built on this 7 Angstrom technology could deliver roughly 7,000 TOPS of performance compared to the 1,500 TOPS seen in current enterprise chips, cutting down frontier LLM training cycles from 3 months down to just 2 weeks. The simulated results of this architecture are staggering. IBM reports that the 0.7 nanometer Nanostack node is projected to deliver up to a 50% increase in computing performance, or a massive 70% reduction in energy consumption compared to today's leading-edge nodes. This brings us to the ultimate question that is shaking the global technology supply chain. What does this mean for the current rulers of silicon, TSMC and Intel? To put this breakthrough in perspective, Intel recently celebrated entering the risk production testing phase for its 1.8 nanometer node. TSMC is aggressively building out infrastructure for its 2 nanometer process. IBM has just leapfrogged both of them by moving the roadmap entirely past the nanometer threshold and straight into the scale of atoms, the Angstrom era. A 0.7 nanometer chip is precisely 7 angstroms wide. Now, it is important to understand the business dynamics here. IBM is a research powerhouse, but they do not operate their own massive commercial factories. They design the blueprints, validate the science, and then license that technology out to global manufacturing partners. In the past, IBM has partnered with companies like Samsung and Japan's cutting-edge Rapidus initiative to bring their designs to life. To turn this 0.7 nanometer blueprint into actual physical commercial reality within the next 5 years, IBM is integrating a specialized, ultra-rare manufacturing tool into their Albany facility. The High Numerical Aperture Extreme Ultraviolet Lithography System, built exclusively by the Dutch monopoly ASML. This machine uses extreme ultraviolet light to print circuits with atomic scale precision. By proving that sub-1 nanometer logic and SRAM scaling is entirely viable, IBM has handed a massive weapon to any foundry willing to partner with them. If Samsung or Rapidus successfully commercializes this architecture, they could completely bypass TSMC's manufacturing monopoly, shifting the center of gravity for high-performance AI chips overnight. Let us look deeper into how this impacts the brutal competitive rivalry between Intel and TSMC. For the last several years, Intel has been betting its entire corporate future on a strategy called 5 nodes in 4 years, culminating in their 18A and 14A nodes. Intel's big marketing angle was their early adoption of PowerVia, which is their version of backside power delivery. Intel believed that by separating the power lines from the data lines on a flat plane, they could squeeze out just enough performance to reclaim the semiconductor crown from TSMC. Meanwhile, TSMC chose a much more conservative path. The Taiwanese giant delayed implementing backside power delivery, choosing instead to stick with refined versions of their flat nanosheet design for their upcoming 2nm and 1.4nm nodes. TSMC's bet was that the industry didn't need radical architectural shifts yet, and that they could achieve scaling through sheer manufacturing precision and extreme lithography optimization. But IBM's 0.7nm announcement blows both of these corporate roadmaps completely out of the water. It proves that simply optimizing flat nanosheets or adding backside power to a traditional flat CMOS layout is like putting a faster engine inside a horse carriage. The true bottleneck wasn't the wiring or the precision of the laser, it was the flat, two-dimensional layout itself. By demonstrating that a vertical 3D nanostack can scale logic density by double while simultaneously shrinking the stubborn SRAM memory footprint by 40%, IBM has essentially shifted the goalposts of the entire industry. Intel and TSMC now face a massive existential dilemma. Do they continue spending tens of billions of dollars building out ultra-expensive factories, optimized for flat 1nm nodes that will be obsolete the moment they open? Or do they halt their current roadmaps, take a massive financial hit, and scrap their designs to pivot toward vertical 3D sequential integration? The stakes could not be higher. If TSMC hesitates, it opens a massive window of vulnerability for its rivals. Samsung, which has historically struggled to match TSMC's yields on flat nodes, has been heavily involved in joint research ecosystems with IBM for years. If Samsung takes this 0.7nm nanostack blueprint and successfully integrates it into their commercial foundries using ASML's high NAEUV machines, they could leapfrog TSMC entirely. They could become the exclusive manufacturer for the world's most powerful next-generation artificial intelligence chips, leaving TSMC scrambling to catch up. Furthermore, this development completely alters the geopolitical chessboard of the semiconductor industry. Right now, the entire global economy relies on a single, fragile point of failure, the island of Taiwan, where TSMC produces over 90% of the world's advanced microchips. Governments across the West have been terrified of a potential conflict that could halt Taiwan's chip supply and trigger a global economic collapse. This fear is what drove the passage of the CHIPS Act, pumping tens of billions of dollars into building domestic factories in the United States and Europe. But building factories is useless if the technology inside them is one generation behind. IBM's research takes place entirely inside the United States, at the Albany NanoTech Complex in New York. By pioneering the sub-1nm frontier on American soil, IBM has provided a technological anchor for Western semiconductor sovereignty. It means that the next major paradigm shift in computing history will not be dictated by geographic monopolies in East Asia, but by architectural innovations designed to be built anywhere in the world. As we watch this incredible race unfold, the absolute limits of human engineering are being pushed to the brink. We are no longer just manipulating silicon. We are quite literally organizing individual atoms like bricks in a skyscraper to prevent the laws of quantum mechanics from breaking our digital world. The companies that realize the future is vertical will dominate the next century of human progress. The companies that stay flat will simply cease to exist. Before you click away, I want to hear your final thoughts on this massive shift. Now that you've seen the raw engineering data behind the vertical nanostack, drop a comment below answering this question. Will TSMC survive the transition to the 3D Angstrom era? Or is Samsung about to steal the throne? Let me know your take down below, hit that subscribe button to join our elite hardware community, and we will see you in the next Deep Tech Breakdown.